Section 17.3, diffraction. So the bending of a wave around an obstacle or the edges of an opening is called diffraction. And this is something we observe all the time without realizing it. One example of this is why sound can be heard more than in a straight line path outside an open door, right? So you can imagine that there's some noise coming from inside this room and there's an open door. Well, if there is no diffraction or distraction, the sound would only be able to travel in a straight line. And if you happen to be standing off to one side, you wouldn't hear a thing, right? So you could be standing up here and you'd have no idea that any sound was coming, right? Because you wouldn't hear anything. But that's not the case, right? If there's an open door and there's noise inside, you can be standing right next to the door and you'll hear something because the sound is actually bending around the edges of the opening. And that's why if you're standing off to one side, you'll still hear a noise. You'll be like, oh yeah, there's something going on inside there. Right? The same idea of why you can hear someone coming around a corner is the sound is bending around that corner. So this is known as diffraction. Sound is the easiest way to observe this. You can observe it with light, and you'll get to see that a little bit in physics 2B. But that only applies to very, very narrow openings. For sound, we're able to see it in our normal frequencies that we have on an everyday case. So this is important to understand what's going on here. So diffraction, why does the sound wave bend? Why doesn't it just travel in a straight line? Well, the key is that there's these individual air molecules in the opening, say the doorway, right? If there's a room that has some sound coming out of it. Each one of those is vibrating back and forth in the longitudinal wave, right? As the sound wave moves to the right here, that causes them to vibrate along the direction of the wave propagation. Each one of them can then become its own source of a longitudinal wave, right? So the one on top starts to generate its own longitudinal wave that's going out in all directions. The one below is doing the same. And there's a whole bunch of other air molecules. We've just drawn two in here for simplicity. What this means is that at the very center, there's a nice maximum, right, with loud noises, if we're talking sound, because we have constructive interference here. But it also means that there is a point on either side of that center where there's destructive interference and where we lose sound. And that's noted by this angle theta, right? Measured from the center out to this point theta. You follow this line, this is where the sound intensity goes to 0, where there's no sound. And it's the same above and below. I equals 0, no sound. So it's very important that we can locate where that occurs, right? Because this is like a cone of sound coming out. And there are cases where you want to be inside the cone of sound, and other cases where you might not want to be inside it. You want to be outside of it. So this equation gives us, if we take sine of that angle, that will give us the first minimum, right? So the first minimum is located at this angle theta. So we could solve this for theta, right? If we take the inverse sine, theta is equal to inverse sine of the wavelength over d. Now what is d here? D is the diameter of the opening. So it is important that it is a D, capital D, for diameter. And specific to whatever opening you have. The lambda then is the wavelength of the sound, which we know we can get, and that will tell us the theta of what angle it bends out to, right? Where we have our theta depicted here. All right, so this is general diffraction. let's think about it in the context of speakers with our sound. Well, with a speaker, you don't just have a vertical opening like the doorway. You have a speaker is usually a circular disc that can vibrate back and forth, a diaphragm. For a circular opening, the equation is slightly different. It's still a sine of theta is equal to something times lambda over the diameter, but now we have this extra 1.22 in front. That's just because it's a circle. You don't have to worry about where it comes from. But this tells us where the first minimum would occur. An important thing to note is this ratio of wavelength over diameter tells us how much diffraction there is, how much the sound will bend outward. So if lambda over d is small, then we get really little diffraction. If instead it's big, then we get more diffraction. So if we want to think about in terms of sound, sound is usually described in terms of frequency. So for instance, if something is a really high frequency, the speed of sound is constant. That's fixed at 343 meters per second, right? So if that stays constant, we want a high frequency. That means we're going to have a small wavelength end result. Well, if you have a small wavelength with a set diameter of the speaker, that means we're going to have a pretty small amount of diffraction. And that's what's shown with this pink curve, that high frequency sounds coming from the speaker aren't diffracted or bent outward, right? They're at a tiny angle of 9.4 degrees. This is known as if the sound isn't diffracted much, it's beamed forward, like turning on a flashlight, right? It's just traveling in a straight line. What that means is you'll be able to hear the high frequencies only if you're able to have your ear inside that cone. So man here can hear the high frequencies as well as the low frequencies that are on this blue cone, right? But a person who's just slightly off center of the speaker can only hear the low frequencies, and she can no longer hear the high frequencies. Those get washed out, right? The low frequencies, turns out, are able to diffract more easily because if we have a low frequency, that means we would have a large wavelength. So a large wavelength means we get a bigger ratio of lambda to d and thus more diffraction. So it bends to a larger angle, which is shown with this 68 degrees. So what do we do here, right? Because it's pretty important that you hear both the low and the high frequencies. Unless you really like your bass, you usually want to have some of the high frequencies in there too. Well, this is why audio systems have speakers with different diameters, right? And if you think of a high-pitched speaker known as the tweeter speaker, it has a diameter that's set so that this lambda over d ratio isn't quite as small, right? To make it bigger, if we have a small wavelength, we're going to need a smaller diameter as well. And so that's exactly how tweeter speakers look, right? If you have a stack of speakers, the tweeter speaker is the tiny one at the top. It has the smallest diameter, and thus for its smaller wavelengths, the higher frequencies, it's able to diffract them to a wider angle so that you can hear those high frequencies throughout the room, not just right in front of the speaker. So this introduces the idea of diffraction with sound. And as I've been saying, there's more cool interference effects to come.